So next, let's see the condition for touching circles. As we know that there are two types of touching circles. One is touching externally and touching internally. So there are two different cases which arise with two different types of touching circles. So if I have the two cases of touching externally and this is touching internally, then with these two cases, let's see how we can derive for touching circles. Now when I clearly see that the two circles, say one with center C1 and other with center C2, and radius of this circle is R1 and the radius of this circle is R2, then clearly I see that the distance between their centers is nothing but sum of their radii, which is R1 and R2. So in order that these two circles touch, the condition is the distance between C1 and C2 must be equal to R1 plus R2 is the condition for two circles to touch externally. Similarly, if I have two circles touching internally, the center of this circle is C1 and the center of this circle is C2 with radius R1 and R2, then clearly when I join these two, I see that the distance between C1 and C2 is R1 minus R2. This minus this gives me the distance between two centers. Therefore, the condition is this equals mod R1 minus R2, whichever is greater. The modulus comes because if the value is negative, we make it positive by putting the modulus. So this is the condition for internally touching circles and condition for externally touching circles. Now let's take the third case of intersecting circles. That is, if the two circles are intersecting, then I have this C1 and C2 and radius of this circle is R1 and radius of this circle is R2, then the distance between the centers is obviously less than the sum of the radii, as can be clearly seen here. Therefore, the condition for this is the distance between the two centers of the circle is always less than the sum of the radii of the two circles. If the distance between centers is greater than the sum of the radii, the two circles are disjoint. If the distance between the centers is less than sum of the radii, the two circles are intersecting circles. Now the next case is where the condition for one circle inside the other, that is, if I have a whole of the circle which is inside the other circle, say like this, with center C1 and center C2, then here I clearly see that the condition for one circle to be inside the other is the distance between the two centers is less than mod of R1 minus R2 is how we understand the condition for whole of the circle to be inside the other circle. The condition is this less than this is how we understand the condition for one circle inside the other circle. Now next is the concentric circles. We know that two circles are concentric if they have same center. That is, if I have a circle which is concentric with this, then that means they have same center. So let me say the center of the bigger circle is C1 and the center of the smaller circle is C2 with the respective radii being R1 and R2 respectively, then for the two circles to be concentric, the distance between their centers is 0, or mathematically we say that the two centers coincide, or C1 and C2 coincide is how we understand the condition for concentric circles. Center of similitude. Now that we have discussed the common tangents for three types of possibilities of circles: touching, intersecting and disjoint. Now let's connect the center of similitude with those three cases of the circles. Now to bring back all the three cases out here, I have so these two are disjoint circles and these two are touching circles and these two are intersecting and these two are the intersecting circles. Now here I have these circles which are disjoint or non-intersecting. We know that we have four tangents which can be drawn for these types of disjoint circles. Now revisiting the common tangents concept, there are four common tangents which I can draw. One is this and the other is this. And let me say the center of this circle is C1 and center of this circle is C2. Then when I join exactly, I see that there are 2 points of intersection of the pair of tangents. One is P and the other is Q. So when the pair of tangents intersect outside the two centers, this point is called the external center of similitude, and if the pair of tangents intersect between the centers, then that point of intersection is called internal center of similitude. So in this case, these two tangents, when they intersect at P is called external center of similitude, and Q is called internal center of similitude. Next, if I have the pair of tangents, we know that there are 3 pair of tangents which I can draw for this. 1, 2 and 3. If the center of this circle is C1 and this is C2, then if I join here, then there are 2 points of intersection. One is P and the other here is Q. So here Q is between the two centers C1 and C2. Q is called internal center of similitude and P is called external center of similitude. So in this case, P is external center of similitude and Q is internal center of similitude, as we can see the case here. Now similarly, if I draw the common tangents out here, the center of this circle and center of this circle pass through the point P, which is called external center of similitude. But in this case, there is no internal center of similitude because no tangents intersect between the centers of circles. Therefore, no internal center of similitude is how we understand the three cases of disjoint circles, touching circles, and intersecting circles through the center of similitude. And also, as I see the second case, there is one more possibility that the two circles touch internally. So in case of the two circles touching internally, then in this case I have the tangent here, which is T, and therefore I have P, which is outside of centers P, C1 and C2. Therefore, in this case, P is external center of similitude. But there is no internal center of similitude when the two circles touch internally. There's only the external center of similitude, which is the point of contact of the tangent with the two circles. Now let's see how to find the center of similitude connected with the given problems, respective problems. Say for example, I have a problem which says find the number of common tangents which can be drawn for the circles x square plus y square minus 14x plus 6y plus 33 equal to 0, x square plus y square plus 30x minus 2y plus 1 equal to 0. So the initial part of the question is this, and also find the external and internal centers of similitude if they exist. Now this question is related to the center of similitude, but before that, the part 1 of the question is to find the number of common tangents which can be drawn for these two circles, and we know that the number of tangents depends on the relative positions of the two circles, whether they are intersecting, touching, or disjoint. So let's see the relative position of these two circles before we find the internal and external centers of similitude. Now as I take the two circles, I have the first circle, which is x squared plus y squared minus 14x plus 6y plus 33 equals 0, and my second circle, which is s dash x squared plus y squared plus 30x minus 2y plus 1 equals 0. Now clearly the center of this circle, if I denote by C1, is minus g minus f, that is minus g and minus f, which is this, and the center of this circle, which is denoted by C2, is minus g 15, that is minus 15, and minus f, which is 1, extracted from gx, 2gx and 2fy. Now that we know the centers of each of the circles, now is the question in finding the radius of each of the circles. If suppose radius of this circle is r1, then this is root of g squared plus f squared minus c. So root of g squared plus f squared minus c is the formula. And then I get this as 49 plus 9, which is 58, minus 33 is 40, 18 plus 17. So 58 minus 33, 30, 40, 18 plus 7, 25. So root 25 is 5. This is the radius of the first circle, R1. Similarly, if R2 is the radius of the second circle, then I have root of G square plus F square minus C. That is root 225, which is 15. So therefore, I have the radius, the radii and the centers through which I am going to find the relative positions of two circles, which in turn gives me the number of tangents. Now I find the distance between the two centers and connect with radius. So therefore, if I want to find the distance between two centers, then I use the distance formula, root of x2 minus x1 whole square plus y2 minus y1 whole square. Plus 7, which is 5, 22. $484 plus 16, which is root 500. That is, therefore, C1, C2 distance is root 500. That is 10 root 5. So clearly I see that this is 10 root 5. And my R1, which is 5, and R2, which is 15, gives me R1 plus R2, which is 5 plus 15, which is 20. So clearly I see that R1 plus R2 is 5 plus 15, which is 20, which in turn is equal to root of 400. So clearly when I see equation 1 and equation 2, from 1 and 2, I see that root 500 is greater than root 400. That implies root 500, which is C1, C2, is greater than R1 plus R2. So as I see the relation with this greater than this implies the distance between the centers is greater than R1 plus R2. That is, this is possible only when the two circles are disjoint, because the distance between the centers is more than the sum of the radii. The two circles must be far apart, disjoint circles. So therefore, this implies the two circles are disjoint. Now when the circles are disjoint, let's see how many common tangents we can draw for the two disjoint circles. So let's take the two circles where the radius of this circle is 5 and the radius of this circle is 15, and this is given by C1 and C2, where the coordinates of C1 are 7 minus 3 and the coordinates of C2, which are minus 15 and 1. So this is the case of two circles which are disjoint in nature. Now as I can clearly see that there are 4 common tangents which I can draw, that is 1, 2, 3 and 4. So there are totally T1, T2, T3, T4. So 4 common tangents can be drawn for the given circles. So, with the conclusion that there are 4 tangents which can be drawn for the given circles is part 1 of the question. Now next comes the part 2 of the question, which wants us to find the centers of similitude. Now we know that for these 2 disjoint circles there are 2 centers of similitude, one being this and one being this. So there are 2 centers of similitude, this being internal center of similitude and this being external center of similitude. So with these 2 centers of similitude, which you're going to find using the centers and the radii, is how we find the centers of similitude. To be continued. Now here, initially to find the point Q, that is the internal center of similitude. So in order to find Q, I utilize the points C1 and C2 and then see how we can do it with respect to the ratio. Now here, the ratio is clearly R1 is to R2, that is 5 is to 15, which is 5 ones, 5 threes. So the ratio of R1 is to R2 is 1 is to 3. Now Q divides C1, C2 internally in the ratio 1 is to 3. So we have discussed in coordinate geometry that if a point divides internally in the ratio m is to n, then we have the formula m1x2 plus n1x2 by m plus n, and so on and so forth, through which you get this. Therefore, in order to find the coordinates of Q, I use the formula mx2 plus nx1 by m plus n. That is, this is x1 y1, x2 y2, and this is your m and this is your n. So using the formula mx2 plus nx1, mx2 plus nx1 by m plus n, and then my2 1 times of 1 plus ny1 by m plus n, which on simplification gives minus 15 plus 21, which is minus 15 plus 7 3 is 21 by 4, and 5 3 is 15 plus 1, 16 by 4, 2 2s, 2 3s, 4 1s, 4 4s, minus 3 by 2, 4. Therefore, the internal center of similitude Q is given by minus 3 by 2 and 4. The internal center of similitude is how we obtain with this. Now next comes on finding the external center of similitude, that is point P. Now next is to find the external center of similitude. I take the same ratio R1 is to R2, which is 1 is to 3, and Q divides, P divides the distance between centers C1 and C2 externally in the ratio 1:3. Now we know that if a point divides externally, then we get the formula mx2 minus nx1 by m minus n. All the plus in between is replaced with minus for external point which we find. Therefore, in order to find p, it is nothing but mx1, where this is m and this is n. So mx2 1 times of minus 15 minus nx1, which is this, by m minus n. So all the plus is replaced with minus in the middle because this is externally dividing in the ratio 1:3. Similarly, my2, which is 1 times of 1 minus ny1 by m minus n is what we get. This, on further simplification, gives minus 15 minus 21 is 26 minus 36 by minus 2, and then 1 minus 15 by minus 2, which on further simplification gives minus cancelled, 2 1s, 2 18s, 2 1s, 2 7s, which is 18, 7. Therefore, point P is 18, 7, which is called the external center of similitude. So this is how we find the internal center of similitude and the external center of similitude for the given respective relative positions of circles, and identify the number of tangents through this example problem. Now let's take the concept of combined equation of pair of tangents. That is, say for example, I have a circle S equals 0. And for this circle, let me say P is an external point outside the circle with coordinates x1, y1. So for a point P outside the circle, that is for P is an external point of the circle, we know that there are two pairs of tangents which can be drawn for the circle. So we have two pairs of tangents, one pair of tangent, that is T1 and T2, which can be drawn from external point. So equation of these pairs of tangents is given by the formula equation of pair of tangents T1 and T2 from Px1 y1 with respect to the circle S equal to 0 is given by S1 square is equal to S times S11, is how we understand the equation of pair of tangents given by the formula S1 square equals S times S11. So equation of pairs of these two tangents together is given by this formula, the pair of tangents with their equation.